Right, so we're going to look at steganography in this presentation. So we'll look at some of the outline methods that we can use. Obviously, there are many methods that can be used for our steganography, but we'll just look at some of the more common methods that are possible. Then we'll have a look at discriminators. Discriminators allow us to determine if there's hidden content inside other content. Then we'll look at some covert channels, such as hiding information within IP and TCP headers. Have a little look at port knocking, and then on to Tor or onion routing. And then finally we'll look at some dictionary codes. Okay, so steganography is really part of data hiding. Steganography involves either technical steganography, as we'll see, or linguistic ones. We can also use things like covert channels, anonymity, as we'll see with our Tor routing, copywriting, where we can put copyright marking and watermarking on, and so on. So we can use the normal encryption and hashing methods if we want to hide data, of course. This presentation won't really focus on these too much, but obviously, just to recap, you have symmetric encryption. We use the same key to encrypt as we could do to decrypt. RC4, RC2, AES, DES, and so on are all private key or symmetric key functions. Then we can have asymmetric encryption or public key, where we have two keys. One key is used to encrypt, and then a separate key is then used to decrypt. So RSA is a good example of this, but we also have LGAMO, which is an elliptic curve method. Then we have hashing functions, which are one-way functions. So it shouldn't really be easy to reverse it back from the hash back to the original data. So we define this as a one-way function. Unfortunately, these suffer from rainbow tables, where an intruder can build a whole table full of the hash values and then reverse that back again. So MD5 and SHA-1 are two common hashing methods. And then finally, we can use encoding, of course. So hexadecimal, base64, ASCII, UTF-16, and so on, all different encoding formats that we can use to represent our binary data in some sort of form that a system can understand. So data hiding and covert channels and so on have been around for a long time. So we see them in the movies, where someone will drop a suitcase on the ground and then someone else will come along and pick it up. We also get things like microfiche and then hidden templates within typewritten text. So here's a hidden message. Can you see what it is? I'll give you a little minute to see if you can find it. Okay, so as far as your eye is concerned, everything looks okay because all the frequency of the letters looks fine. It does look like a sentence. When you read it, it doesn't really make that much sense, but it might mean some sense to someone. But obviously the hidden message here, hopefully you found it, involves the first letter of each of the words, and it should say, "Let the message begin." Okay, so that was the kind of method that was used before electronic communications, but now we can be more sophisticated with our data hiding. So here's an example. Okay, this is a contraband image, so we're not meant to have this image. What's one way that we could hide it? Well, of course, what we could do is to take the PowerPoint file and then just place another image on top of it. So as far as anyone looking at this slide, the image doesn't actually exist, but it's still there. It just happens that we've actually just placed that one on top of it. The image itself is still in the file, and probably when we look at the file, we can actually still see the contents of it, its file name, its metadata, and so on. And here's another example here. Can you find where the file is, where the graphic is? Is it there? There, it's there. Okay, we could shrink an image right down to 1 pixel and you wouldn't even see it. So it could be as small as that, even smaller, a single pixel on the screen. So there's our image there, and as you see, we shrunk it down to a single pixel and it can be seen. So spammers use this technique all the time. When you receive an email, you'll actually find that there's a graphic file in it. The graphics file is 1 pixel in width and height, but the link to it goes back to the server which sent it. So when the user reads the email, they don't see the single pixel there, but that does a callback onto the server, and if it's all linked together, if the graphic has a certain unique ID associated with it, then the spammer can tell if the user has actually read the email and at what time. Okay, so here's an example. Many different formats that we actually have, such as PowerPoint, are encapsulating formats. They'll take a graphic and then embed it into the actual source here. So you can see it here. So this is the original file with inside the PowerPoint. It's our PowerPoint file when we look in hexadecimal. And we can actually see the name of the file is actually in there. What we do see is, you see here the letter and then a 00, an ASCII character 007300. What this is actually 16-bit encoding. So 16-bit encoding takes the ASCII character, such as, say in this case, the C, and it represents it with 005F. So that becomes a 16-bit value. Okay, so the original data might be 8-bit, but sometimes it gets converted into 16 bits to actually allow for more characters. So what are some of the methods that we might use for our steganography? Well, one way is to use the noise. So every file doesn't have every little bit having some sort of information which is really significant. So there's a whole lot of extra information that we get in a file, and we typically call that noise, not really that important. So what we can do is we can add some information into the noise so that it's not actually seen by the user. We can spread the information out, so we could put something like having a word on every page, and then that would then all bind together to give us our message. Okay, and then we could take some sort of structural information to make it look like it's normal, a normal document, but hide information. In this case, I've taken some football results here. Manchester United 0, Manchester City 1, Celtic 1, Aberdeen 0, Liverpool 1, Stoke 0, Hearts 0, Hibs 0. So it's a fairly low scoring day, and the reason it was a low scoring day is that these are actually binary values. Okay, so I've hidden a little message here, 0, 1, 1, 0, 1, 0, 0, 0. That is 64 in hex, 64. We'll just check what that is. Okay, so we'll just bring up our ASCII coding just to see if we can find what 64 is. So 64 hex, if we go right down, here we are here. Okay, no, sorry, it was 68. 68. It was 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, and it was a 68 hex, which is an H. So this here, 68, because we have a 1, 0, 0, 0, is actually the character H. We could also change the order of something like a shopping list, and then we could put eggs. If we put eggs up the top, then it's a 1, and so on. We can split the information across different documents, such as as we said, the first word on every page. We can hide the source of the information, as we'll see with inside our Tor onion routing. We can also use a statistical profile, which tricks the user. This was like what we've seen before. When the user looks at this, everything looks okay. it has all the normal probabilities of letters, but actually see, if we take the letters there, it prints out hello. And then we can replace some randomness, such as imperfections in a photograph. So obviously you wouldn't see these, but we could put spots here on David Bowie's face, and this would be a 0, 1, 1, 0, and then a 1, 0, 0, 1. It looks like that is an eye. Okay, as our first example, let's have a look at some JPEG hiding and how that actually works. So here's a JPEG image, and what I've done here is I've actually added in some text into the image, and you can actually see that it's almost impossible to see any changes in the image. And this is because normally we split the image up, and we'll be seeing this in a little minute, into pixel blocks, typically 8 by 8, and then we take a frequency analysis of each of these pixel blocks, and we store the frequencies or the changes of the pixels within inside the blocks. Most of the time when we zoom into a block, there is very little change, so most of the information is actually what we call the low frequency end of the pixel block. But if we then go and stuff our hidden information up in the high region here, then you'll find the changes won't actually be seen because they only affect one small little pixel block, and also there are high frequency changes, so it won't change that much. And this is the change here. This is all that's really happened to the image. If we zoom right into it, you can actually start to see the pixel blocks within inside here, and you can actually see there is a small change in this one pixel block. So let's have a look at some discriminators that we have within inside our information that we could actually spot when something is hidden within inside something else. So we'll take a quick example, and we'll take an example of JPEG first to see if we can actually spot that. So as we said, a JPEG image, such as this one here, gets split into 8 by 8 pixel blocks. Okay, so here they are. And then what we do is that we take a frequency or a spatial analysis of each of the 8 by 8 blocks, and then we represent them here. So there's the first one, second one is there, and so on. And this one here is the highest changing of all. That's 7, 7 here, and you can see that's a checkerboard. That has the highest change of the pixels of all of them. Okay, so we do that a little analysis, and then we end up with numbers like this. Okay, and then what we do is that we then what's called thresholding. So we threshold, and we divide it by a certain number, and then find the closest integer to them. Okay, so in this case we've divided by a certain value, and then these are the values that we actually get at the end. And there we are there. Okay, one thing to notice is that we see a lot of zeros here, which is very typical for our pixel blocks. Then what we do is that we store them in this zigzag format. Okay, and that allows us to actually create a whole lot of zeros, sequences of zeros, because all these are typically zeros. So we use what's called Huffman coding here. We'll see that in a little minute. Huffman coding allows you to take a popular value and represent it with a small code, and then from there we can use what's called zero length encoding. And zero length encoding allows us to say that there are 4 zeros in a sequence, and use that as a single code. Okay, so here's our JPEG. There's our JPEG there. The starting point of a JPEG is FFD8. FFBB, BDB, you can see is the quantization table. There's another one there. And FFC0 is start of frame, and so on. So often what we can do is we can actually find these tags, these binary values, hexadecimal values inside a file. If we detect these, there's a very good chance that we've actually found a JPEG. One thing that we can look for is the value of FF00, because sometimes in our data we actually have a value of FF and we don't want it confused with these tags. So what happens is that in JPEG we stuff a couple of zeros after the FF if it's a real FF. So we've done a process here on a file and then found out in what block it's the Huffman is actually in. Each block is 512 bytes long, so we see it found in block 2, 7, 8, 10, 11, 13, 14, 15, 16, 17, and so on. So from this, if we actually find FF00 inside a small 512 byte block, then there's a very good chance that we have a JPEG image. And especially if we find all of these tags typically near the start of the file, then we definitely know that we have a JPEG image. Okay, so here's an example here. We've taken some segments there, and then we can see it's found in most of the 512 byte blocks. There is some sense that FF00 is actually there. Okay, only in these ones here did it not find a stuffed value. Another example of a discriminator is with MP3 files. MP3 files store a whole lot of audio samples in a frame, and then we add on a header at the start of the frame, so that you can actually start really whenever you want to be able to synchronize. So you can start at any point within the audio and then read the header, and then you can take the data from there. So we have what's called the MP3 Sync, and that's 12 ones together. We then get a fairly standard format of the version, MP3 layer, and so on, so that we can make sure that what we're reading is actually an MP3 file. So here's another example with an MP3 file. What we're looking for is 4 ones together as a sequence, looking for 11 bits or 12 bits of ones together. And you can see here it's found it virtually in every one of the segments that we've been looking for from them. Okay, so we could probably detect the presence of an MP3 file if we can actually detect all these ones together in any of the samples that we would take from the file. Okay. Another typical method that's actually used is what's called least significant bit hiding. So with this, what happens is that your eye really isn't very sensitive to small changes of colour. So colour is typically made up of R, G, B. Each one is 8 bits from a value of 0 to 255 or 0 to FF hex. Okay, so white is made up of full red, full green and full blue, or 255, 255, 255, or FF, FF, FF. Okay, this is defined as a 24-bit colour. Okay, and it gives you more than enough colours than you actually need. It gives you over 1 million colours there that are possible. We can also use CMYK, that's another method for that. But typically our graphics are stored in this RGB type format. So what we do with least significant bit modulation is that we take the least significant bit, in this case the blue, and we change the least significant bit if we need a 0 to a 0, and if we need a 1 we change it to a 1. So in this case 50 is 0, 51 1, 1, 0, 1, 0, 0, 1. Okay, so that's our, sorry, 0 there. That's our message there, which is an H value. And that's been hidden with inside this part of the image there. So when we look at the hexadecimal, we can actually see this actually happening. So there you go. So this is a 1, 0, 1, 1, 0, 1, 0, 0, 0. And what's happening here is this is what's called the color table here. So the colors that are used, the 24-bit colors, remember there's 3 values here, 3 8-bit values are actually modified in some way. But the modification is so small that really your eye can't see the difference. Another way is to just change the least significant bit of our values for our audio. So let's say that I had an intensity of 200. We can change it to 201, and that would represent a 1, or we could leave it at 200 if it was a 0. So with the least significant bit of audio, then we can do the same kind of thing, in that your ear wouldn't really hear the difference between the least significant bit changing or not. So now let's look at hiding with inside message block. So we've seen how we can hide it with inside some colors. Let's see how we can apply this to a practical example. So this is the format of a GIF file. So we have GIF89AD is the first few bytes that we actually have here. And then we have 2 bytes which represent the screen width and the screen height. So if we think about it, they are here. Okay, that's little Indian. So this is the least significant byte, and this is the most significant byte here. And that defines the actual width of the image. Then what we get is a definition that we're going to have a color table. And then after a couple of bytes here, we actually have 256 different or 256 3-byte colors, the RGB colors. Okay, then we can see what's happened here is that I've added in hello into the global color table. So the global color table is this bit here. So this is defining all the colors that are inside the image here. Okay, so these colors are used with inside the image to actually define the different colors. So with GIF we can have 256 colors of 24-bit colors, no more than that for the global color table. But you can see what I've done is I've actually added in the word hello, and it's not changed the image too much. Actually, you'll just see around the edges there's a few extra little pixels and so on. But what I've done here is that I've obviously modified one of the colors so that the one of the colors obviously has a significant effect. Okay, so we can also get hidden messages with inside documents, such as what's been found on Xerox printers. So this was an example that EFF analysed, and we can see there are dots, and the dots actually represent when the printhead was, when the output was actually taken, and also the printer type. We can also get static messages with inside video. So we can get subliminal messages in there. Advertisers use this quite often in their products. Okay, so if you watch quite carefully, see if you can spot anything.
Our next guest is getting quite a bit of attention this afternoon. That is because he has managed to figure out how to replace the AT&T chip in an Apple iPhone, which means, of course, you can use your iPhone on another network. George Hotz of Glen Rock, New Jersey, joins us now, and it is so great to see you in person because it's amazing what you have done.
Okay, so I hope you saw that.
Our next guest is getting quite a bit of attention this afternoon. That is because he has managed to figure out how to replace the AT&T chip in an Apple iPhone, which means, of course, you can use your iPhone on another network. George Hotz of Glen Rock, New Jersey, joins us now, and it is so great to see you in person because it's amazing what you have done.
Okay, so
Right, our next guest is
here we
getting
go.
quite a bit of attention this afternoon. That is because he has managed to figure out how to replace the AT&T chip in an Apple iPhone,
There.
which means, of course, you can use your iPhone on another network. George Hotz of Glen Rock, New Jersey,
There.
joins us now, and it is so great to see you in person because it's amazing what you have done.
Okay, so there was by Coca-Cola in there. You might not have seen it if the message is actually played if the time for the message is actually quite short, then you typically don't perceive it, but your brain will certainly be able to register it from there. So that's an example of hiding some static images with inside our video content. So let's look at how we can hide code in our messages. Okay, so for this one, what you've got is a couple of codes here. So you should be able to use your QR code for the one at the top right hand corner. Okay, so if you just go ahead and you install it onto your phone, and then go ahead and scan the QR code at the top right hand corner there. The other code that we have there is what it's called the Zapper code. So if you go to the Zapper code, Zapper app for your mobile phone, then you should be able to determine the actual video that's associated with this code. Okay, so it's possible to hide images with inside valid content. We see here at the very top there, we can have a very small image and the QR code is still valid if it's zoomed. And this one here could be attached to t-shirts or stuck on the wall or something like that. And we can get full content from them. Okay, so let's now look at when something is embedded into a file, and we often have to use file carving for that. So with file carving, we have something deep within data. It might not come up when we search for it, and we've got to do a byte by byte scan of the disk. Okay, so this shows our example of our GIF file again. So there's the GIF in there, and so on. If you remember, this is all our color table with inside that. So there are certain key markers that we look for. GIF, or in hexadecimal, that's the equivalent. For JPEG, it's FFD8, or for the metadata, GIF %PDF for a PDF file. The end of the PDF is %EOF. Then there are various other ones that we can actually look for. Here we see our new formats, and these here are actually zip files. So this is the header that we would get from a normal PK zip format. Okay, so there we go. That looks quite like a PK zip file. Okay, so there's a RAR is in there too, and so on, TIFF, and there's Flash. So we often look for a header and a trailer to be able to carve out the file from inside our text. Okay, so it's possible for somebody to change, say, the file extension from a JPEG into a DLL, and if we're searching for JPEGs, then we won't be able to find that one. But we certainly will be able to find the GIF and FFD8. There we go. There they are there. We should also see the FF00 and other types of tags. There's the NFF tag there. There's another one. And so on. When we're into the data, we should be able to see the FF00s in there. Okay, so as we've seen before, the metadata typically gets kept whenever we insert our data into a file, in this case with inside PowerPoint. Here's an example of a zip file. So we can see here, that's the standard header for our zip file, our pkzip here. There it is. Okay, little endian. And then there is a fairly standard format that we have, but what you can see is that we can actually see the names of the files and the header of our zip file. A good package that we can use to be able to carve out sort of images and documents and so on is Scalpel. So we'll have a quick look at Scalpel, see what actually it shows us. Okay, let's see if we've got a disk here. Yep. So what we've got here is a raw file from a raw format, which is really just the disk in its raw form from a Canon camera. I think some images were deleted from it, but it's possible to carve them out from here. So with Scalpel, what we have is a config file, and the config file defines all the different types of formats that we want to carve out. Okay, so we'll just have a look at that one. So there's a GIF. So a GIF file has this header and this trailer. Okay, at the very end of the GIF we get 003B. For a JPEG file, as we've seen, we get this FFD8, and then FFD9 is the end of it. There's a PNG and so on. Just in case the trailer has been lost on the file, it's been deleted, then we have a maximum size. So we'll just keep carving until we hit this value here. Okay, so it has a whole lot of other types of formats that we can actually see in there. So what we'll do is we'll see if we can get Scalpel to run. And we'll just go for this file here, and we'll just output it into my new folder. Okay, just let me run it from my bin. Okay, so you can see here it's found some JPEG files and also some GIF files there. There's the doc file, PDF file, and so on. So we can actually go in and have a little look. Let's see the file we created, my new folder. And there we are. Okay, so there's all the images it's actually found. Let's see if any of them will view. No. Okay, so it's carved all these out, so it's possible to go in and get the files out. We'll just try it with the other one just now, just to see if there's anything on the second one. This one. Okay, so we'll try that one. This time we've got a whole lot of documents. So let's see if we can actually have a look at these. And so we'll have a look at the JPEGs. Okay, so we can actually see these are real JPEGs, and it's managed to carve these out very well. Just small images there. This one's a bit larger. Okay, so it's managed to get the JPEG files, a PDF file. There we go, so it's got that one. Okay, so that's in there. Okay, so the file carving allows us to be able to effectively scan our drives, carve files out of data. So we'll just have a quick look there. So if we want to actually have a look at the raw file, and there. Okay, so this is the one we've just been looking at. Okay, so this is what we would get on a disk, and then obviously we'd be looking for the FFD8. the FF, look for FF. Just select it all. I want to search them. There we go. Okay, so we want to search for our FFD8. Search them. There we go. Okay, so there's the first image there. Search for the next one. And there's the next one. Okay, so you can see that what we can do is that we can often analyze our data, and then we can actually search through the hex values looking for our data in them. So if we wanted to look for, say, a hex string, then we can obviously look for something like PDF. Okay, so we obviously need to look if it's either an 8-bit or a 16-bit. So there's our %PDF there, and hopefully we'll be able to find the EOF for the end of that, and then it's there. Okay, so there's the PDF file contained within inside our content. Okay, so it's a useful package to be able to carve out data from within inside other data. Now let's look at two different coding formats which are often used with inside steganography or data hiding. One is a very popular method called Huffman coding, used in a lot of graphics formats. What it does is it represents the most probable sequence as with the shortest code, and the least probable with the longest code. So let's take an example. So we can see here the most popular letter is an E followed by an I. So what we do is that we order them in their sequence numbers, and then we actually put them in a table here. Okay, so this one here is actually C. Okay, so what we do with Huffman is that we start with the bottom two, and then we allocate the least with a 0 and the second least with a 1. We then add them together to give us 15, and then a 15 and a 20 is the next two, then a 1 and a 0, that becomes 35, we'll give that one a 1 and that's a 0, and then so on. And then the way we read is we go from here backwards. So an E in this case is going to be a 1, 1, an I is going to be a 1, 0, and so on. So these are the codes that we end up getting from them. The great thing about Huffman is that we don't need to have fixed widths. We can automatically tell the character just by reading the bit sequences. Okay, 0 can't be anything. 0, 1, yeah. No, not yet. 0, 1, 0, 1, 1 is a P. And then 0, 0 is an O. And then 1, 1 is an E. Okay, so Huffman is used fairly extensively in processing. Here's an example here. Okay, so the boy stood on the burning deck. Okay, so normally that would take, you count the number of characters in 8 bits per character, take quite a lot of space to do that, so we'll just analyse that. And there's what we're encoding it with. Okay, this is our code here. And we've managed to decode it there. Okay, so you should find some test examples here if you want to give them a try. You can see this one is very efficient. There are only three characters in there, and we're representing the T here with a 0. Then we have a 1 0 and a 1 1. Another popular operator that we can use, typical encryption, data hiding, is the exclusive OR. So exclusive OR, a 1 and a 1 gives us 0, 1 0 gives us 1, 0 0 gives us 0, and so on. The great thing about exclusive OR is that we don't actually lose any of the information when we apply it. And we apply the same thing twice, we get the original data back again. So in this case, we're taking Napier, and there's the Napier string, and we exclusive OR it with T. Okay, there's our T there, and this is the output that we actually get. Okay, so we can't represent it in ASCII because it will give us non-printed characters, so we either represent it in hex or base64. So you can see there's the output actually there. We'll exclusive OR it again with that, and we should be able to get back to the original value that we have. Another thing that we can actually do is to be able to do a rotate left or a rotate right. So a rotate left goes that way, a rotate right goes that way, and a rotate left goes that way. The bits that come off the edge at the end go back to the start again. Okay, so I can show you an example of this one. If we go back to our coding, and then we go for our XOR. There's our XOR. Okay, Fred. There we go. Okay, so if we take the character E, there is the encoded string. Okay, that's our Fred there. There's the E there, and then there's the result. Look what happens when we take the same letter and exclusive OR it, we get all zeros. Okay, so that's the encoded value, and all we have to do again is to be able to exclusive OR the output with all these again, and we get back to the original. Very, 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 very simple, but very effective. And it will often scramble things like magic numbers and so on. So now let's look at two extremely important methods, and that's lempel-viz or lempel-viz Welsh, which is LZW. That's the compression method which is used in many systems, graphics, zip files, gzip and so on, all use this lempel-viz method and run length encoding. So it's similar to what we looked at in terms of Huffman coding, but what happens is that we scan the system for a dictionary. So it comes up with all the words that or the common pieces of data, and then builds these into a dictionary with an index. So in this case, we'll take a space, we'll take the word "the boy stood on," and then a dot and end and so on. Okay, so now if we want, if we store this, that becomes 00001, that becomes 00, that becomes 03, and so on. So we store the dictionary at the start of the file, and then what we do is we create a pointer to that dictionary, and it will effectively reduce the amount of data. So in this case, this has got 7 characters in it, but we're only representing it, say, with a binary value. So that this would be represented as a binary value at the start of our file as an index. So it compresses greatly, but it can also be used for data hiding. It's also used in image type of compression. So we can see here that images often have areas which are the same. Same with video. So video often has the same image, or this. When you look at, if you watch a football match, you actually find that only a small region of the actual video is actually changing from frame to frame. Often what we get is a full frame in video, and we'll only get like an update frame, and then the full frame comes through again. But between the images, very little is actually changing, and the same with inside an image. you can see in this slide here, all these areas here are actually the same as the one previously because they're all just big white pixel blocks. Same over here, and this one for those ones. So RLE will take that as sort of the LimpleViz would take that as an object and then actually define it in a table. So what we've got is a 1, a 1, a 1, 1, 1, and then a 2 here, and then a 1. RLE encoding comes in, kicks in, and actually will say we want 4, or in this case 5 1s, and then we want a 0, 2, and then we will have 5, and then we have a code which is saying 5 1s, and so on. And this massively compresses down the amount of data that's actually used. So this can be used for data compression, but it can also be used for data hiding, where we can create a dictionary of terms and then inside that data, especially if we divorce the two together, that one was stored somewhere and that one's stored in somewhere else. We'd have to match the two up to be able to recover the data again. Another area that's possible to be able to hide our data is within what's called zero knowledge proofs. And zero knowledge can be defined as the 2 millionaire, or in this case 2 billionaire problem. So what we have is 2 billionaires that get together and they don't want to tell each other how much money they've got, and they don't trust anybody to be able to tell them because they think they'll go and tell someone else. So the 2 billionaire problem in this case is, how does Bill Gates and Richard Branson talk to each other? And at the end of it, Bill Gates will actually realise that he has the most money. So this is to do with systems that do not have a trust network, such as an online auction system where someone might vote and then we end up with the vote which is the highest or the highest bid, but we don't reveal any of the other bids at all, and not even the winning bids. So an example of this is the S-secure function evaluation, SFE. So in this case, what we're doing is preserving the original number of votes that were cast by Bob, Alice and Carol. If we next take 3 random values, Bob is told to take 3 random values and then take his vote and plus 100. Okay, so Bob creates 3 random values which give the sum of his vote plus 100. Okay, so if we add up these values there, so that becomes 95, add 7 becomes 102. Okay, so 102 is the correct value. Alice does the same, so she needs to get to 102 also. Okay, so these 3 values she takes randomly and then and then we'll create them. Carol needs to get to 108, so she takes 19, 14 and 3. Okay, so both Bob, Alice and Carol have 3 values that they're going to share now, and each value is their vote plus 100. So if you got one of them, you couldn't really work out what the other 2 was to be able to find the total number of votes. Even if you got 2, that still wouldn't be enough. Okay, so now Bob gets Alice's second value, this one here, 44, and Carol's second value, and then adds his first value and takes the sum. Okay, and then Alice takes Bob's second value, and Carol's third value, and then adds it to her own first value. Okay, so then we get that, and then the Alice does the calculation here. Next, they can all get together and tell each other what they found. So Bob says, I got 130, Alice said, I got 68, Carol says 114, and then they get the total of 312. We now take a mod of 100 and we end up with 12, which amazingly is the number of votes that were cast. Okay, so obviously it's more complicated when we get real life systems, but that shows the principle of what actually happens, and that we can actually create these shares which don't actually give away the information. This type of system is used where we actually don't want to reveal any of the core information, like what age are you 18 or over, and then some data is passed, and the system can actually determine if you're over 18 without you actually giving the actual core data to the system. Another method that can be used for secrecy and for steganography is port knocking. Port knocking is all about connecting on different ports in a certain sequence, and then the connection is open up. So in this case, port 99 knock, port 199 knock, and then a connection is made up, is created between the two sides. A similar type of method to the zero knowledge is with secret shares. And secret shares is a bit like a pirate problem. So in this case, we've got 4 pirates who don't really trust each other. So they agree that they're going to share this treasure map with X marks the spot. And what they want to do is to be able to create something so that if, say, 2 of the pirates got together, they could actually reveal the map. Okay, so in this case, what we can do is create a sharing system, and we can have a number of share thresholds. So 4 is the number of shares in this case, and the threshold we've decided is 2. 2 pirates can get together. So Aldi Shamir came up with a method of secret sharing where we can actually create the shares. In this case, there's the 4 shares, and then 2 of the shares can actually come together and actually reveal the original data. So we should be able to have a look at that one from them. That's in our encryption. And then we'll look at Shamir. Okay, there are other secret sharing algorithms that are more efficient than this one. This one is based on creating an equation. If you have 2 points on a line, then only by bringing those 2 points together can you actually determine the equation of the straight line. Okay, so we just get connected. X marks the spot. Okay, so we've got 4 pirates, and we're going to do any 2 from 4. And there we are. Okay, so what I've done here is I've taken 2 of the shares back and then got the original data back. Okay, so you can see there's no cryptography going on here, and this really will hide the information. So you would really have to bring back at least the number of shares together to be able to get the original data back again. So this type of method is actually quite interesting from many points of view in modern cryptography or modern data hiding, in that it doesn't actually reveal, by getting any of the shares, doesn't actually reveal the other information that we've actually stored. So the method, as I said, uses the if we have 2 points in a line, then only by bringing the 2 points together can we actually calculate the gradient of the line. We can go for more complicated quadratic equations and so on, and take points in the line, and only by bringing together the actual points, those points, can you actually reveal the original information. So this could be something like data striped across different clouds. So it's possible for, say, 4 cloud providers. We take our original data, and then what we do is store them into a different cloud provider, so that if 2 of the cloud providers went down, then we can actually still get the data back again. Okay, but obviously in a steganography point of view, this is an almost perfect steganography. What we'd do is we'd hide one part of the data someplace, and then another part of the data somewhere else, and only the person who knows how to build the data can actually bring the 2 shares back together again. Another thing about steganography is to be able to hide the original source of the information. And one example of that is obviously with onion routing or Tor routing. We can use something like a proxy to be able to hide the original source. But the onion routing protocol gives us a good example of hiding the anonymity of a source. So in this case, what we have is within a Tor type network, the nodes themselves can be part of the network and provide routing agents to be able to get from Bob to Alice. So there's a negotiation about the route that will be taken, and then each of the machines involved obviously have a public and a private key that they can use. So in this case, this node has a purple key, this one has the green key, this one has the red key. So the keys go back, and then when Bob is sending Alice the data, he will then encrypt with the data with the red key, then with the green key, and then with the purple key. So then if it goes through, then this node should be able to take the purple key off. So what we'll end up with is a red and a green here. So this is the encryption again, and then encryption on the skin. So this now has two encryption keys on it. It will then go through the green node, and the green node will be able to take this one off. So the last route, it will have the red, and the red key will take its key off, and then the data between here and here will be unencrypted. The IP address, which actually appears here, will be this node here, and not this one over there. This method is a little bit like a hasp. So if you were working on a piece of electric equipment, you might put the hasp on, and then you would put your own padlock onto the hasp. So other people can come along and put their padlock on. So you can take the padlock off. It's still not. You still can't actually open it until all the padlocks have actually been taken off the hasp. Okay, so that shows the principle of Tor routing. So perhaps we can actually see an example of Tor in operation. So this shows an example of using a Tor browser. So we went to this website here, and we actually see the log on the server is this. Okay, so that comes from one of the routing elements in the chain, and if we use a non-Tor browser, we actually see this is the core IP address. So Tor hides the end, the complete chain, and we only see the end gateway out of the Tor network, and that's the IP address that actually appears then. Along with this, what happens is that we get a different browser too, so that the end of the Tor connection will not represent the actual browser that's used by the client. Okay, so that explains really how onion routing actually works and how we can preserve the original source. And now let's look at covert channels. So covert channels are another method that someone might use to be able to send some secret information. It's typically used where someone or two parties are being observed greatly, and some messages need to be passed without the observers actually seeing the information. The two main methods we can actually use for this is we can use a storage channel. So what we can do is we can write some data which can be picked up. We can maybe modulate we can store the file on a system where both suspects have access to it. Okay, so I could put a message there, and then that message could be read by the other person. The other way is to use a timing channel. So we might modulate the CPU. So the CPU goes up to 100% at at 5 past the hour. So the other suspect can view that and say that's a 1. And then the next hour it might be 0%, and then that's a 0. It's modulated back up to 100, that's a 1, and so on. Okay, and that's known as a timing channel. One place that we can hide information is inside some of the fields within the IP and the TCP protocol. We can also hide it at the higher layers, but IP and TCP tend not to be examined for the information that they actually contain. So some of the areas that, some of the fields within the IP that isn't really used that much, identification, TTL could be used as long as we don't set it to 0, and fragment offset. So information can be put in here. This is 16-bit long, so we could put an H and an E in there. We could put an L and an L there, and we could put an O in there, or we could use each just one at a time. Within TCP, the data offset and the urgent pointer really aren't used that much in there, and things could be hidden in there. So as far as someone observing, everything looks fine, and we can't actually see anything. Another area that we have a sequence number for our TCP packets or TCP segments, and the sequence number just has to be unique within a certain time window. So different operating systems will create different sequence numbers, and what we see, so this is an example of the variation of the sequence numbers within TCP. So it's varying greatly there. But various different types of operating systems change the numbers that they have for the sequence numbers. So we can see here that Windows is just incrementing that value each time for each segment, where Linux is taking big jumps quickly. Sun Solaris takes a jump every now and then and does a random value, and OpenBSD takes a big jump and then does an increment a long time. So we can actually pinpoint the different types of operating systems from the values that we get inside the identification of the TCP segment. Okay, so here's another couple of examples that we see. And this one here, we can actually see that there could be a secret message or some stenography actually in this one, because the variations just seem a little bit strange. And here's the example here. So we see there's our identification field. So it's incrementing, and then just all of a sudden it's actually jumping from there. Okay, so we can actually have a look at some real packets, hopefully, from there, and see if we can actually have a look at that field. Just run a little bit slowly from there. Okay, so just have a look at network forensics. And let's see if we can look at our Ubuntu one. Let's just open that one up. We just have a little problem with that one. So we'll try another one. So we'll just go for this one here. Okay, so there's our identification field here for IP. So watch, so it's changing, and then it took a jump there. Okay, did you see that? So we went there, and that's the one coming back. So we just, so that one, so it's still going up in a sequence. That's a sequence there, and so on. So it's not jumped at all. Okay, there we are back. So you can see that the identification field will typically be a sequence number that we'll actually get, and you can actually trace to actually see what happens to that, but we can often profile the operating system based on that. Okay, so that's an example where we go in a sequence there. But this one here, for the IP identification field, we can see there's the jump. Okay, that takes a jump there, where the ID field just changes very quickly. Okay, so I've tried to outline some of the methods that might be used in steganography. There are a whole lot of other ones, but this at least has given you a little bit of thought. Okay, thank you.